So this is the first lecture over chapter 20, over nuclear chemistry. So we'll give a little introduction and brief review of some material from Chem 1311, which will help you understand this chapter. So of course you remember the basic structure of the atom. I have a nucleus, electron cloud, and in the nucleus the protons and neutrons, and the electrons and the electron cloud. So you can write like a nuclide symbol, right, for sodium 2311, so that would be a nuclide symbol. And if you remember how to interpret nuclide symbols, the bottom number is number of protons. It's atomic number, right, given the symbol Z. And so 11 protons in the nucleus, and the top number is the mass number, which is number of protons and neutrons. So if you 23 minus 11 is 12, so there would be 12 neutrons in the nucleus of the atom. And then typically what would be wrote here is the net charge. So if there's nothing wrote there, then there must be 11 electrons as well, right? Or if it was plus 1, then there would be only 10 electrons and 11 protons and 12 neutrons. And if you remember what isotopes are, so isotopes are atoms that have only differ in the number of neutrons in the nucleus. So H1, for example, hydrogen 1, so maybe you see it wrote like that. So if somebody says hydrogen, probably talking about hydrogen 1. So it just has 1 proton and 1 electron. Hydrogen 2, also called deuterium, would have 1 proton, 1 neutron, 1 electron. And hydrogen 3, which would be tritium, has 2 neutrons, 1 proton, and 1 electron. So they all have 1 proton, so they are all hydrogen. They're isotopes of hydrogen because they have different numbers of neutrons in the nucleus. So some elements occur as only 1 isotope in nature. So for example, fluorine occurs as only 1 isotope in nature. Hydrogen occurs as 3 isotopes in nature. And they may all be stable, or they may, and what do I mean by stable? That means non-radioactive, or some may be unstable, meaning they're radioactive, which is what this chapter covers. So for hydrogen, for example, hydrogen 1 and hydrogen 2 are stable, but hydrogen 3 is not. Right, it's radioactive, so it will over time decompose to something that has a more stable nucleus than hydrogen 3 has. Okay, so what's the difference between a chemical reaction and a nuclear reaction? So in chemical reactions, they only involve changes in the electron cloud of the atoms. So if we took an example, so if you take lithium and react it with fluorine, so lithium 7, right, it's got 3 protons, 4 neutrons, and 3 electrons. So of course, if you remember, 1s2, 2s1, 2 electrons in the first shell, 1 in the second shell. And fluorine 19 would have 9 protons, 10 neutrons, 2 electrons in the first shell, 7 in the second shell. So if you remember all this from Gen Chem 1, so if you mix the two together, what happens is basically that the outer shell electron of lithium goes to fluorine, and now lithium only has 2 electrons, so it's a Li plus cation, and fluorine now has 10 electrons. So now it's F minus, so you change the electron clouds in the molecule, whether that is by making ionic compounds or by sharing electrons and making covalent bonds. But nothing happens to the nucleus of an atom in a chemical reaction. So what's the difference between that and a nuclear reaction then? In a nuclear reaction, it's the nucleus of the atom that undergoes change, and it's not affected by the electron cloud. So often in nuclear chemistry, the electrons are totally ignored because they're not important. So radioactivity of tritium, for example, hydrogen 3, is the same whether the tritium is an H2 or it's an H2O. Tritium is going to go exactly the same nuclear chemistry, irregardless, at exactly the same rate. Does not matter what the temperature is, does not matter what the pressure is, does not matter what the concentration is. An unstable nucleus is going to do what it's going to do, independent of everything else. So for that reason, then, electrons are typically just ignored in nuclear reactions. Okay, so there are 118 elements known. So elements 1 through 92 are found in nature, so they're naturally occurring. Elements 93 through 118 are synthetic. So 118 minus 92, so that means there's 26 synthetic elements. And all of them are radioactive. None of them have stable nuclei. Some of the elements 1 through 92 have radioactive isotopes. So not all of them are stable, although most of them have at least one stable isotope, but not all of them do. So elements 93 through 118 are what's called the transuranium element, right? Element number 92 is uranium. So all the elements after uranium are the transuranium element. They're all synthetic and they're all radioactive. So they will all undergo the chemistry that we talk about in this chapter. Okay, so for the discovery of radioactivity, so it was discovered in 1896, and this is the basic experiment that was done. So if you took a block of uranium minerals from nature, it emits radiation. And if you put in front of that block of uranium a block of lead, because lead absorbs radiation, but if you have a hole in the lead block, then radiation, one beam of radiation can come through that lead block. And so then if you push that radiation beam through an electric field, what's found is that some of the particles, some of the radiation is deflected towards the positive pole of the electric field. Some isn't, so those are what are known as beta particles. So they're negatively charged. So if they're negative, they're going to be attracted to a positive. Right, some radiation is not deflected at all, so it goes straight through, and so it hits the photographic plate, which is how it's discovered, because there's areas on the photographic plate that were discolored. So it was figured out then that something was hitting the plate at those points. So something's not deflected at all. Those are gamma rays. So gamma ray is very high energy, very short wavelength, so typically of about 10 to the minus 12 meter wavelength. And then some of the radiation is deflected towards the negative pole of the electric field, and those are what are known as alpha particles. Okay, so what is a beta particle? A beta particle is basically an electron. So it's an electron ejected from the nucleus of an atom. So what is an electron doing in the nucleus of an atom? Well, we'll talk about that a little bit later, because electrons, of course, are supposed to exist in electron clouds. But it is possible that an electron can be created in the nucleus of an atom and then ejected from the atom at a very high speed. And so that's what's known as a beta particle. And so what is an alpha particle? So an alpha particle, so the symbol is this. So it's basically just the nucleus of a helium atom. So of course in Chem 1, when we saw, if we see this, we would write the structure of the atom as 2 protons, 2 neutrons, and 2 electrons, because it has no charge shown, so it must have the same number of protons and electrons, right? Well, that's what an alpha particle is. An alpha particle is just the nucleus of a helium atom, so it's just 2 protons, 2 neutrons, and no electrons. So technically has a 2+ charge. So technically an alpha particle is it's that He4, 2 protons, 2 plus charge. But again, in nuclear chemistry, electron clouds don't matter, so the charges are typically not shown. So when it's wrote like 4He2, it's just understood that's an alpha particle and it has no electrons, so technically it has a 2 plus charge, it's just not shown. Okay, so alpha particles are very dangerous because He2 plus, helium, of course, has a very high ionization energy. It does not like to lose electrons. So if it's missing 2 electrons, it's going to find 2 electrons, and whatever it comes in contact with, it's going to take 2 electrons from it. So it's going to ionize whatever it comes in contact with because it's going to remove 2 electrons from it. So that makes alpha particles extremely dangerous because whatever it comes in contact with, it's going to take their electrons. But alpha particles are easy to stop. They can be stopped by several sheets of paper. Clothing, skin is enough to stop an alpha particle. But if ingested, then they can be very dangerous because then they can come in contact with internal organs and that can do a lot of damage. Okay, so beta particles, they're very dangerous as well. More dangerous in the sense of alpha particles because they can penetrate skin. They can go through paper, clothing, they can penetrate skin down to about the bone. They're stopped by about 0.5 centimeters of lead. So in the sense that they're more penetrating, they're more dangerous. But in the sense that if alpha particles are ingested, they're more dangerous because of how ionizing they are. And then gamma rays are the most penetrating. They can cause DNA mutations, so they can cause cancer. So it needs about 10 centimeters of lead to stop a gamma ray. Okay, so in this chapter we'll look at 2 different types of nuclear reactions. We'll look at what's known as radioactive decay. So we'll look at 6 examples. 6 different types of radioactive decay. And then we'll look at nuclear bombardment reactions as well, which is also what's called transmutations. So this is how the synthetic elements are created by transmutation. Okay, so there are 6 different things that can be ejected from the nucleus of an atom in a nuclear reaction. You have protons. So given the symbol 1 superscript P subscript 1 or 1H1. Neutrons. So 1, 0. So the superscript is equals the number of nucleons. What is a nucleon? It's a proton or neutron. And the subscript is charge. Of course, protons are +1 charged. So this is different than nuclide symbol, where the subscript represents the atomic number. For the particle that's ejected, that's not what that means. It just means that's the charge of the particle. So a neutron, of course, has no charge, but it is a nucleon. So the superscript is 1. Or you can have an electron ejected from the nucleus of an atom, in which case no nucleon, symbol is E, and its charge is -1. Okay, or you could have what's known as a positron ejected from the nucleus of an atom. So a positron is basically same mass as an electron, but has +1 charge. So it's kind of the opposite, or an anti-electron, opposite of an electron. So 0 superscript, no neutrons or protons. Symbol is E, but the subscript is +1 because it's positively charged. Right? Or you could have an alpha particle emitted from the nucleus. So its symbol. So 4 superscript, helium, subscript 2, would be an alpha particle. And again, if you just keep in mind, it's really something that's +2 charged because it has no electrons. Okay, so how to write a nuclear reaction. So this would be an example of a nuclear reaction. So uranium-238. So if you remember when it's written like that, that's the mass number. And so that's the atomic number and the mass number. Okay, so uranium-238 is radioactive, so it decomposes. So what type of nuclear reaction does it undergo? Well, one of the products is an alpha particle, so it undergoes alpha emission. So it gives a thorium-234 and an alpha particle. So when you write nuclear reactions, one thing you have to keep in mind is that the sum of the superscripts on the right has to equal the sum of the superscripts on the left of the arrow. So the mass number, just total mass number, has to stay the same. And then same is true for the subscripts. If you take the subscripts 90 and 92, it has to equal the sum of the subscripts on the left of the arrow as well. Okay, so this could be useful if you keep that in mind. So if you're given a nuclear reaction like this, for example, Ra-226, it decomposes by alpha emission, so it gives off an alpha particle as well. So what is it that it decomposes to? So what is the superscript, what is the subscript, and what is the element symbol Y? Well, how do you figure that out? Well, you start with a mass number of 226, so you have to end with total mass number of 226 on the right. So 226 minus 4 equals 222. So whatever x is, it must be 222. And then the same is true for the bottom. So you start with a mass number of 88, atomic number of 88, or the charge on the bottom is 88. So 88 minus 2 is 86, so the number on the bottom must be 86. And so how do you know what element that is? Well, you look at a periodic table and look up what is atomic number 86. And so that would be Rn. So now you have the complete nuclear reaction. So 226 Ra, 88 decomposes to Rn, 222 86 plus an alpha particle. Okay, so that's a basic introduction to nuclear chemistry. So in the next video, we'll cover the 6 different types of nuclear reactions that we'll look at.